What if a problem from way back in 1900, one that seemed pretty much solved, actually held a deep secret about the quantum world? Today, we're doing a deep dive into just that. There's a new paper out in Physical Review Research by Clougherty and Dinh. They've taken this old classical idea from Lam and given it a really fascinating quantum twist. So our mission today is to unpack this quantum Lam model. We want to see what it tells us about, quantum mechanics fundamentals, maybe even future tech. Okay, let's get into it. First, the classical part. Imagine this really simple picture. A tiny vibrating particle, maybe like a bead on a string, and it's interacting with its back in 1900. Lam studied how the waves created by this vibration would actually damp it, slow it down. He was really interested in how this classical damped harmonic oscillator worked. Right, and what's amazing really is that his model, this bead connected by a spring to a long string under tension, it came way before quantum theory. Like it completely predates it. It's such a fundamental picture of how systems lose energy to their surroundings. It really sets the stage. Okay, so that's the classical picture, pretty clear. But now let's jump forward to today. We bring in quantum mechanics into it. What happens? How does this simple bead on a string change when you look at it quantumly? Well, new paper introduces a quantum version of Lam's model, and the really cool part is they show it's exactly solvable. They use this sophisticated technique. It's called a multimode Bogoliubov transformation. A Bogoliubov transformation. Okay, what does that actually do here? Think of it as a mathematical tool. It helps untangle complex interactions, especially when you have many things interacting, like the bead and all the modes of the string. It simplifies the problem enough so you can find an exact answer, which is honestly quite rare for these kinds of open quantum systems. It gives us a really clean model, a sort of theoretical lab for studying damped quantum oscillators, things like quantum decoherence even. Okay, exactly solvable? That's a big deal in quantum physics. But what do they actually find? What's the surprising part about the system's most basic state? Its ground state. The ground state? Yeah. The lowest energy state. It turns out to be what's called a multimode squeezed vacuum state. A squeezed vacuum state. That definitely sounds like science fiction. What does that mean practically? For a little bead, why care about that? It does sound sci-fi, I agree, but it's very real. Squeezed states are actually a key resource in quantum technology. Think about precision measurements, like gravitational wave detectors LIGO, for instance. They use squeezing to make incredibly sensitive measurements, basically by reducing the quantum noise, the uncertainty in one property-like position. Okay, so connecting it back to this Lam model, they found the bead's position uncertainty, even in its lowest energy state, gets smaller as the damping increases. Exactly. That feels completely backwards from a classical point of view. More damping usually means more randomness or noise, right? It does seem backwards classically, absolutely, but quantum mechanics has the Heisenberg uncertainty principle. You can trade uncertainty between pairs of properties like position and momentum. You can squeeze the uncertainty out of one, but it pops up in the other. What this paper shows counterintuitively is that the interaction with the environment, the damping, can actually cause the squeezing in the ground state. This is a beautiful reminder that quantum rules can be very different from our everyday intuition. Really fascinating. Okay, so besides the ground state, the paper also looks at the dynamics, right? How the vibrations actually fade away. Yes, they look at the decay process. If you imagine the string, the environment, being infinitely large, the bead's vibrational energy can just radiate away completely. And they managed to get a precise mathematical formula, a closed form expression for how quickly this happens, the damping rate. And how does that compare to the old classical result? It agrees perfectly with Lam's classical result when the coupling between the bead and the string is weak. That's a really important check. It shows the quantum model connects back to the classical world where it should. Okay, so the energy radiates away, but what is carrying it? Is it like quantum waves? Sort of. The decay involves the emission of these specific excitations they call Bogoliubons. These aren't fundamental particles like electrons. They're more like collective wiggles, quasi-particles that emerge from the whole system interacting. They carry the energy away, and they can even calculate the probability of emitting, say, just one of these Bogoliubons during the decay. So this isn't just a theoretical curiosity about a bead then. It has broader implications. What's the real takeaway for you here? Oh, definitely not just a curiosity. This model, because it's exactly solvable, provides a really solid framework. It could be applied to understand related quantum systems, maybe local vibrations in certain magnetic materials that could be relevant for quantum information stored in solids, or even systems where you couple something to an electromagnetic cavity. Those are building blocks for quantum computers. The bottom line is understanding how to precisely model and control this kind of energy dissipation, this damping, is crucial. It can help us design better quantum sensors, maybe more stable qubits for quantum computing. It gives us a new theoretical tool. So we started with this seemingly simple century-old classical problem, the vibrating bead. And looking at it through a modern quantum lens gives us these exact, profound insights. Things like squeezed vacuum states, these Bogoliubons, new ways to think about energy loss at the quantum level. It really shows the enduring power of physics, doesn't it? How revisiting old questions with new tools can open up new unexpected avenues. It really does. So it makes you wonder what other familiar classical systems might hold surprising quantum secrets if we just look hard enough. And how could those discoveries change what we think is possible with technology? What really stands out to you about this link between old classical physics and the quantum frontier is something to think about.